Welcome to this Maths Made Easy video on composite and inverse functions. To start with, let's take a look at the language of functions. Now there's some key terms that you need to understand before we look at composite and inverse functions. A function is an operation that maps each number to only one number. So for example, if we have x cubed, then we could write this as f of x equals x cubed. Another way of writing this is using the following notation, like so. However, these are equivalent, but you might also come across this notation here at the bottom. The domain is the set of input or starting values, and the range is the set of possible output values. The domain and our range is usually the set of real numbers, and we denote this using this notation here, okay, which you might already be familiar with. And remember, this is just representing any number, decimal, fraction, surd, etc. And if x is any real number, then we write this as x belongs to the reals. Okay, so we use this notation to represent that. A function that maps one element in the domain to one element in the range is called a one-to-one function. And a function that maps more than one element in the domain to one element in the range is called a many-to-one function. So let's take a look at this example here, where we want to state the domain and range of the graphs that we can see on the screen here. So let's just clear what we've got on the screen so far. So if we want to state the domain and range here of these functions, well, we've got f of x equals 3x and g of x equals x squared. Well, to start with, both functions have domain. So for the domain then, so for both functions, let's write this out in full then. So both functions have domain where x belongs to the reals. Okay, so that's for our domain. And for the range then, if we just change this to represent it in a different pen colour, well, for the range, f of x, this is for the range, well, f of x has a range of f of x belongs to the reals. Okay, and we can see for f of x that this is actually a one-to-one function. And for g of x, so for g of x then, this has a range of g of x being greater than or equal to 0. Okay, and this is a many-to-one function because we can see if we input 2 and we input minus 2, we obtain the same result. We get 4 for both. 2 squared is 4, and minus 2 squared also gives us 4. So g of x is a many-to-one function. So that gives us everything we need there for the language of functions. Moving on now to take a look at composite functions. A composite function is a combination of two or more functions, say f and g, and this creates a new function. And we write composite functions as, for example, f g of x. Okay, and what this means is that we do g first and then do f, and we can rewrite this as f of g of x. Okay, and this can make things a little bit clearer to see. But it's important to note here that the order is extremely important. In most cases, f g of x will not be equal to g f of x. In other words, these will be different functions. And you may also see squared functions, for example, f squared of x. But this is equivalent to f of x. Okay? In other words, you do f twice. So let's take a look at an example here. So, if we have the function f of x, which is equal to 5x squared, where x belongs to the reals, and g of x, which is equal to x minus 1, and again x belongs to the reals here, let's find a few composite functions then. So let's find, for example, fg of 3. So let's do these in different pen colours. So let's start with fg of 3. So how would we do this? For a composite function like this, remember, we start with g first. So this is g of 3. So if we calculate g of 3, that's 3 minus 1, So this becomes f of g of 3, which is equal to f of 3 minus 1. So this is equal to f of 2, and in that case that becomes 5 lots of 2 squared there, okay, which in that case is 5 times 4, which gives us 20. Okay, so that's our first solution there. Let's take a look now at GF3. So just to highlight this here, that FG of x is not equal to FG of x is not equal to GF of x. So GF of 3. So in that case, we can write this as G of f of 3. Okay. In that case, this becomes G of so what are we up to? So G of f of 3. So this is equal to G of 5 of 3 squared here. So just substituting this 3 into f of x. So we close this bracket here, and this is equal to G of 45. And in that case, if we evaluate G of 45 then, well that's just G of 45 is equal to 45 minus 1, giving us 44 there. Okay, and clearly we can see then that FG of 3 is not equal to GF of 3. Okay, 20 is not equal to 44. If we take a look at another one now, let's say f squared of x, so f squared of x. How would we do this? Well, in this case, this is going to be f of x. Okay, just like we mentioned before here, this is f of x. So in that case, this becomes 5 lots of 5x squared all squared. Okay, if we evaluate this, we simply obtain 125x to the 4 there. Okay, and finally then, let's say we want to find fg of x. Okay, so very similar to what we had for our first example here, but this time notice we have g of x rather than g of 3. So we have to go about an algebraic method. So here we're looking for f of g of x. Okay, well here this is f of x minus 1. Remember, g of x is just x minus 1. So it becomes f of x minus 1, which we can write as 5 lots of x minus 1 all squared there. Okay, and that would give us the solution to fg of x there. So that gives us everything we need there for composite functions. Moving on now to solving composite functions equations. You may be asked to solve equations involving composite functions. For example, fg of x equals 2. So here we would just find fg of x and then rearrange and solve to find x. So if we take a look at this example here, we have f of x equals x squared and g of x equals x plus 2. And we want to solve fg of x equals 4. So here, what would we do? Well, the first thing we want to do then is find our composite function, fg of x. So g of x we calculate first, and that goes into f. So in that case, we can write this as fg of x, which is equal to f of g of x, which we can write then as f of x plus 2 here. So f of x plus 2, but f of x is just x squared. So in that case, we just obtain x plus 2 all squared. So in that case, this is fg of x, so therefore x plus 2 all squared is equal to 4. So in that case, we could take the square root then of the left hand side and the right hand side, which would give us x plus 2 is equal to plus or minus 2. Don't forget the negative solution here. And therefore we obtain two solutions. X is equal to minus 4 or x equals 0. Okay. And if we wanted to find the range here, it would be helpful to draw the graph of fg of x. And if we draw this, we can see it looks something like this. Okay. So therefore the range here would just simply be, so for the range, for fg of x, well this will simply be greater than or equal to 0 there. Okay, so that gives us everything we need there for solving composite functions equations. Moving on now to inverse functions. An inverse of a function does the opposite of that function. The inverse of a function, say f of x, is denoted as f with a little -1, like so. Okay, so pretty much the same, we just have a little -1 there, and that denotes the inverse of f of x. An inverse function maps an element in the range to an element in the domain, the opposite of what a function does. Hence, only one-to-one functions have inverses. The domain of the inverse is the same as the range of the function, and the range of the inverse is the same as the domain of the function. A composite function of a function and its inverse, and vice versa, gives x, i.e. f inverse of f of x is equal to f inverse of x, and they are both equal to x. Okay? And to work out the inverse of a function, you need to rearrange the function and change the subject. So let's take a look at an example now. Okay, so we've clear everything so far. Well, let's say we want to find the inverse of f of x equals 2x squared plus 5, with domain x greater than or equal to 0. We want to state the domain and range of our inverse here of f of x. So the first thing we do is we replace f of x with y in the equation. So we write this as y equals 2x squared plus 5. The next step now is to rearrange to make x the subject. So if we start rearranging here, we get y minus 5 is equal to 2x squared. Well, if we divide by 2 now, we get x squared, so y minus 5 over 2 is equal to x squared. And finally, x here is equal to the square root of y minus 5 over 2. And because x is greater than or equal to 0, we don't need the negative square root. Step 3 here, we replace x with f inverse of x and y with x. Therefore, f inverse of x is equal to the square root of x minus 5 over 2 there. And for step 4, we swap the domain and range. So the domain of f of x is given as x greater than or equal to 0, and its range is f of x greater than or equal to 5. So therefore, the domain of the inverse of f of x, so f is minus 1 of x, this is x greater than or equal to 5. And its range, so the range of the inverse of f of x, well, this is simply greater than or equal to 0 there. And a quick note here, for simple functions, you can work out the inverse by looking at it. So for example, x minus 2, so f of x equals x minus 2 here. So let's just actually rewrite that so we can see it clearly. So yeah, like we said, if we've got a simple function, f of x, say x minus 2, well, we can do this by inspection. The inverse here simply given as x plus 2. Okay, so that gives us everything we need there for inverse functions. And finally, moving on now to drawing inverse functions. So for a function f of x plotted on a graph, its inverse, f, so the minus 1 of x, is its reflection in the line y equals x. So if we take a look at this example here, given that f of x is equal to x squared minus 1, with domain x greater than or equal to 0, we want to sketch the graph of the inverse of f of x. Okay, so here, the first thing we do is we just draw f of x with this restriction here on the domain. So if we draw that, we then reflect this in the line y equals x. So putting all this together then, what we get is something that looks like this. Notice here, this red part of the curve is y equals f of x, and this blue part here is y equals the inverse of f of x. This grey line here is y equals x, and this is what we're reflecting. So everything underneath this curve maps above, everything above maps underneath like so. Okay, and that's simply how we sketch the inverse there of f of x. Now the inverse function is simply given as f inverse of x. In this case, this is equal to the square root of x plus 1. Okay, and that would just be, found by finding the inverse here of f of x like normal. And we can see from the graph that f of x has domain x greater than or equal to 0, and that restriction was imposed there. And the range here for f of x is f of x greater than or equal to minus 1. Now for f inverse of x, so the inverse of f of x, well, the domain here is x greater than or equal to minus 1. And for the range here, for f inverse of x, well, the range is simply f inverse of x is greater than or equal to 0 there. Okay, so that gives us everything we need there for drawing inverse functions, and that concludes this mass media video on composite and inverse functions.